In this video, I will be introducing exponential functions and then talking about the calculus of exponential functions. Exponential functions are defined as the following. An exponential function is a function of the form f of x equals b to the x, where b is a positive constant and x is any real number. You realize that exponential functions seems to have some kind of base b, where b is always positive and x is always a real number. I want you to pay attention, this being a function. So this whole thing, f of x equals b to the x, represents a function where x at the exponent is basically your input, and then the result, b to the x, is basically your output or your y value. And then here it might be useful to see the distinction between, for instance, f of x equals x squared. You guys notice here this is a polynomial function, and polynomial functions have exponents to be positive integers, so n, so this is always positive integer. So your variable is not at the exponent, but your variable is algebraic. The base is the variable or the input. But with the exponential functions, you realize input is the exponent and output is what you get using that b to the x. So here it might be useful for us to realize some of the properties of exponentials. So if x is a positive integer, b to the n equals b times, and then you realize this represents n many b's. So you multiply n many b's and then get b to the n, and then a simple example is 2 to the 4th is the same thing as 2 times 2 times 2 times 2, so you multiply 2 by itself 4 times. B to the 0 is always 1, so any number raised by 0, so for instance if you have 5 to the 0, it has to be 1. The value that takes is always 1. And if x is negative n, so in other words, if the exponent is a negative number, then you can write it as b to the negative n equals 1 over b to the n. Or you can also say this could be rewritten as 1 over b raised by n. So the whole thing raised by n is another way of saying it. Okay. Now I want to take a look at an example of how exponential functions actually look. So here I'm going to investigate g of x equals 2 dx and h of x equals 2 to the negative x. So you realize, let's take a look at some input-output values for g. So like for g, let's take a look at some x and y. So if x is 1, then y is 2 to the 1, which is equal to 2. If x is 2, then you get 2 squared, which is 4. If x is 3, you get 2 cubed equals 8. Similarly, if you have 4, then you get 2 to the 4, and that needs to be something like 16. So you can try different values here and see it for yourself. So for h of x, though, the graph might look different. I guess here on the left hand side we can continue with the negative numbers as well. So let's take a look at some negative numbers for g. What if we try negative 1? So it'll be 2 to the negative 1, which is equal to 1 over 2. If we do negative 2, you get 2 to the negative 2 which is equal to 1 over 2 squared, which is equal to 1 over 4. And if we try negative 3, then we get 2 to the negative 3, which is equal to 1 over 2 to the cubed, which is 1 over 8. Okay? And if we do a similar amount of work for 2 to the negative x, if we explore some input-output values for this function, we're going to see if x is 1, so then you get 2 to the negative 1, which is 1 over 2. If x is 2, then you get 2 to the negative 2, which is equal to 1 over 2 squared, which is equal to 1 over 4. If x is 3, then you get 2 to the negative 3, which is 1 over 2 to the cubed, which is equal to 1 over 8. Okay, so if you do negative numbers, though, so if you do negative 1, for instance, you get 2 to the negative of negative 1, which actually results in 2 to the 1. If you get negative 2, then you get 2 to the negative of negative 2, because we're doing negative x. Then you get 2 to the positive 2, which is 4. If you try negative 3, 2 to the negative of negative 3 equals 2 to the 3, which is equal to 8. Alright, so you may realize some kind of pattern here between these two graphs or tables. You realize that positive numbers for the input for 2 to the x actually is the same thing as negative input for this 2 to the negative x function, and then similarly negative values for 2 to the x results in these rational output, which corresponds to positive input for this function 2 to the x. So it would be interesting to see actually how the graphs would look like on a coordinate plane. So if we were to try to graph the first function, you realize all exponentials are gonna pass through y equals 1. So the reason for that is when x is 0, b to the x is always b to the 0 equals 1. So y-intercept for all the exponential functions is always 1. So they all has to pass through 1. So we need to plot that point. So the first graph will be when x is 1, y is 2. So when x is 1, y is 2. When x is 2, y is 4. When x is 3, it's 8. So I'm just going to show a few points here. When x is negative 1, it's going to be 1/2. I'm just going to show 1. So, and then when x is negative 2, it's going to be 1 over 4, which is a really small value here. Okay. All right. So when you plot these points, you're going to realize the graph will actually look like something like this. And it keeps growing. Just going to extend this a little bit. Okay. So you realize this graph belongs to y equals 2 to the x. If we similarly try to plot 2 to the negative x, you realize when x is 1, you get 1/2 here. When x is 2, you get 1 over 4, so smaller value here. When x is 3, then you get 1/8. It's very small value. And then when you look at negative inputs, if it's negative 1, then you're at 2. When you're at negative 2, you're at 4. When you're at negative 3, you're at 8. So then what you realize here is that we have to pass through 1 as well, because when x is 0 for this guy, you're also getting 1. So you have to pass through 1. So you realize the graph actually looking like this. So that's how y equals 2 to the negative x look. So you guys realize we graphed both of these functions, and then both of these functions seems to be symmetrical. And so let's list out some of the properties. Some of the properties of the graph. Realize they're symmetrical, they're one-to-one because they both pass the horizontal line test that I introduced in my last video. Symmetrical. And then I guess, yeah, those are kind of what observations we're making based on the graph. So next I'm going to talk about 3 situations for exponential functions based on the value of the base constant. So you realize when b, the base, is in between 0 and 1, as in the previous case what we had was f of x, the example we looked was 2 to the x, and the other one was 2 to the negative x. You realize with the negative exponent we're actually getting 1 over 2 to the x, which is the same thing as 1 over 2 raised by x. So negative exponent produces the b value in between 0 and 1. So it's always going to be some kind of fraction between 0 and 1. So when that is the situation, then your graph always looks like this, which is what we had previously for 2 to the negative x. It looks like that. And then for when b equals 1, here you realize b is always 1, the base is 1, then you're always getting this linear line because it's a horizontal line. 1 to the x, well, no matter what x is, you're always going to get this same line, y equals 1. And then when b is positive, so when b is like 2 to the x, or like example could be 5 to the x, you're always going to get a function that looks like this diagram. There are a couple of things we need to point out here though. What I want you to realize is exponential functions have certain characteristics. So for instance, one of them is their domain. So their domain could be anything. So you could input any kind of x number from negative infinity to positive infinity. When you consider their range is always from 0 to infinity. So exponential functions do not take negative y values. They never go below the x-axis. They're always above the x-axis. So that's another thing we need to keep in mind. They're always above the x-axis. Okay. What else? So what about y-intercept? So I briefly mentioned that they always have the y-intercept being x equals 0, y equals 1. They always pass through this point. As you guys can see, in all the 3 situations, they always pass through that point. You realize the diagram on the left, when it is a negative exponent or when b is in between 0 and 1, the function seems to be always decreasing, right? The function is always decreasing. And with the opposite situation, when b is positive, you're always realizing that the function is always increasing. And then this function is always constant. So that's another thing we should keep in mind. One other thing I need to mention is that y equals 0, or the x-axis, none of these exponentials will ever touch. So therefore, we're going to say y equals 0 is always a horizontal asymptote. It's never going to touch it. And lastly, all these functions are always continuous. There's no hold, there's no break, there's no jump, nothing like that. Now we take a look at some of the laws of exponents. You may remember from your previous algebra classes, but when you have a base raised by x plus y, you can always separate it as b to the x times b to the y. If you have b to the x minus y, you divide them, so b to the x minus b to the y. If you have b to the x raised by another power, you always multiply them. If you have two bases multiplied, a times b raised by x, then you can separate it as a to the x times b to the x. A quick example of this would look like, so say 6 to the x. I know that 6 could be written as 2 times 3, so I'm just separating the 6, and then I can now apply the property and say 2 to the x times 3 to the x. So these laws help us deal with some of the problems.